Welcome to my talk. Thank you all for coming. Declarative style in C++. I'm going to try and tell you some of my thoughts about that topic. The first thing to say is that this isn't a functional programming talk. This is a talk that tries to fit a declarative style in C++ as we know the language today, i.e. a multi-paradigm language. It's generally the case that most general-purpose programming languages resist categorization in terms of functional or object-oriented or what have you. C++ is certainly procedural, functional, object-oriented, generic. So the topic of declarative style applies to all of those things, in my opinion. So I'm going to try and look at the history of programming in C++ and current practices that we try to follow, and try to tie that together under the umbrella of declarative style. I also want to avoid being sort of hand-wavy. I want to give some practical advice as to what we can do to sort of engage with declarative style. The first thing to say is that declarative style, according to Wikipedia, expresses logic without describing control flow. There's an idea that removing control flow complexity is important, that perhaps ordering of statements or replication of statements should not affect the semantics. And these ideas are key to the promise of declarative style, that when we write in a declarative style, it's easier to convince ourselves that the code is correct. I'm not going to be doing any proving, but I hope to convince you that the code is more correct under a declarative style. So what are some indicators of declarative style? It's not a hard and fast thing, but in general, we like functions to be pure. We like to say what's happening, what we want to happen, as opposed to how we want that to happen in detail. We like to minimize imperative style, that is, managing state and updating state. To be etymologically reductive, declaring things is a good part of declarative style. And it's one of the key ideas to my mind is the idea of using expressions over statements. So this is a preference of style in the service of reasonability. Now, if we look at expressions versus statements, the standard actually has a lot to say about expressions. If you look at expressions in the standard, it says this: an expression is a sequence of operators and operands that specifies a computation. And then it says expressions have some properties. We know that they have, for example, value categories and values and types. So expressions have these intrinsic properties that we can reason about. If we look at statements in the standard, well, we'll get to that in a second. But this idea of expression properties is what gives them composability. So if you consider this snippet, where at could be any operator, plus, minus, what have you. This is an expression is composed on multiple axes. So A, B, and C are themselves expressions. We're composing them together. Of course, they compose at runtime because they all have values, and expr has a value. But they also compose at compile time because they all have types, and expr has a type. So we can reason about this composition. We can check it at compile time. Contrast this with statements. What does the standard say about statements? Not very helpful. Except as indicated, statements are executed in sequence. And statements aren't given the properties that expressions are. The standard goes on to list the kinds of statements you have, but the statements are defined in that way extrinsically rather than intrinsically, as expressions are. So in particular, statements compose by sequencing them, right? And there's no direct way that we can constrain this. Now, we do some value checking with asserts, maybe. But we have a lot of brainpower that's actually gone into checking this composition of statements. We have varyingly implicit constraints with our pre- and post conditions, variable lifetime extents. We use variable scoping to control things. But at the end of the day, so Dijkstra, that famous curmudgeon of computer science, said, our intellectual powers are rather geared to master static relations, and our powers to visualize processes evolving in time are relatively poorly developed. When you think about it, many of our guidelines, and perhaps many of the things you've heard at this conference, are in service of trying to figure out how to wrangle this composition of statements. We put a lot of effort into it. We make conventions, we make guidelines, we make tools. We like to run multiple kinds of tools to get different benefits from each. We make libraries in support of those tools. We add things to the language like contracts to help us manage this problem. There are lots of great minds working on this problem, bringing formal reasoning to statement flow. And that's fantastic, all well and good. But an alternative to having to deal with this big mess of temporal statement flow is to try and use fewer statements and more expressions, which will give us more reasonability. So a declarative style is, to my mind, a preference for avoiding statements. Here are some kinds of statements that C++ have. It's not an exhaustive list. For the language lawyers, you can go on CppReference.com and look up a few things I left out. But these are the lion's share of statements that typically occur in a program. Expression statements and declaration statements may be sort of an expressive style, a declarative style. The rest of them actually, declaration statements are good in a declarative style, I guess we could say. But the rest of them we should try and minimize. And I hope to show, although this sounds odd at first, when we look at current practice and guidelines that we have and look at them through a declarative lens, we'll see that minimizing statements is in many cases what we're already doing, even if we don't realize it. So let's take a little look at history, where we've come from, see how it informs this picture. Here is a famous bug. Many of you probably recognize it. So I'm first attacking here assignment, because it's the king of expression statements. And there are two odd things about assignment. The first odd thing is that assignments are expressions at all. The idea of expression statements and assignment as an expression statement is a strange thing, and I don't think it's doing any favors today. Some languages make a hard distinction between expressions and statements. C++ doesn't. In C++, expressions are statements too. So C++ is a so-called expression-oriented language, and many languages, this isn't a new thing in languages. This was true of Algol 68 and Lisp. So we need to go back a bit in time to find kind of where this came from. Okay, anyone know what language this is? And as a clue, I had to tell my syntax highlighter that it's C. It's not C. It's actually, yes, it's actually B. This is from, you can look at the Wikipedia page on B. This is from the user's reference to B by Ken Thompson. B was descended from BCPL. B came around in 1969, BCPL 1967. BCPL had an assignment command, not an assignment expression. But when Ken Thompson wrote B, he decided to make assignment an expression. As you can see there, A equals N over B. That's an assignment, but it's also an expression being evaluated as part of the if. So assignment as an expression is odd. We've learned to deal with it, but we don't really like it. And to deal with it, we have things like Yoda conditions. It used to be a thing. Now we have compiler warnings, so Yoda conditions aren't so much used. We have things like, recently, PO 963 was a proposal to make structured binding declaration admissible as a condition in an if statement, a lot like assignment is. But that was discouraged. So I think this shows that we get along with assignment as expressions, but we don't really, that's not the way we like to think of things. Okay, here's the same snippet of B, and here is the second odd thing about it. Now, I put in, on that line, if A equals N over B, I didn't have that comment there before, and that comment is in the original source. The fact that equals means assignment and not a test for equality, of course we're used to this today, but it's worth asking, why do we have equals meaning assignment and double equals as equality? This wasn't a thing that Niklas Wirth was a fan of, and he made it quite clear. because it overthrows tradition. He wasn't really a fan of operator overloading. But we'll come back to that. So how do we get to have equals as assignment? Well, in 1951, CppCon introduced equals for assignment. This was an incredible time for programming language innovation. CppCon also introduced the for loop. And then when Fortran came along, Fortran was on machines with very restricted character sets. They didn't have a greater than sign, a less than sign, etc. And so it had to use these strange incantations for greater than, less than, equal to. Using those for comparison freed up the equal sign to be used for assignment. And so on and so forth. Algol 58 introduced colon equals as distinct from equality, and many sort of languages that derive from things like that went that way. And then in 1967, BCPL used the same thing. But then B came along, and B is really responsible for a lot of the choices that, I mean, Ken Thompson made them in 1969. They were carried forward to C. They were carried forward to C++. B is basically responsible for almost all of the operators we have in C++ today. Now, Ken Thompson had good reasons for doing that. This was one of his reasons, although I would like to challenge this view today. Assignment being about twice as frequent as equality testing makes it appropriate for assignment to be half as long in operator length, was what he said. Now, his reason was that he needed to fit BCPL, basically, on the PDP-7. Now, in 1969, the BCPL compiler took about 16K of memory, which is amazing to think of these days. And the PDP-7, which was the new kid on the block, had just 4K of memory. So Ken did an amazing thing. He cut down BCPL from 16K, and he made B, and he made it fit into that 4K. But it did mean that he had to cut anything he could. And so we ended up with equals, meaning assignment, among other things. So the distinction between assignment and declaration was blurred at that point. But we shouldn't forget, indeed Bjarne said, assignment and initialization are very different operations. All right, enough history. What we learn from history is that declaring things has always been fine. And declaration and assignment happen to look the same, but they're very different things, and we should think of them differently. Assignment as an expression is a sort of lazy convenience that doesn't really do us any favors today. And expression statements have always been, in that sense, a trap for the unwary. That's why we have things like if initializers, no discard attributes, all these things we put into the language and in the compilers to help us deal with this idea of assignment as an expression. Now, I know some people at this point might bring up that, oh, well, assignment is an expression because you can chain assignments, and that's rather nice. Well, I grepped a multiple 100,000 line code base for chained assignments. I found 0. That tells me that we, at least in the kind of code that I work in, chained assignments aren't really a thing we use, they aren't a thing we need to use. All right, so here are our statement types. I'm going to be attacking each one. And assignment's starting to look a bit shaky. We'll be coming back to this table as I go through the talk. Now let's make a quick declarative study of a snippet of C++ that, and see how we might rewrite it in a more declarative style. So here's the piece of code. As you can see, it's very small. Given that we have, let's say, a weak putter to foo, how would we lock that and get something out of the foo? Here's one way to do it, and this way is a perfectly fine way. This would probably pass code review in many code bases I've worked in. And with without a declarative style, without really thinking about how to do it differently, this is a great way to do it. This is taking several guideline boxes. We've got lifetime scope on the shared putter, so it doesn't live beyond when we need it to. But it's still unsatisfying. We've got a declaration initialization split here. We have to declare bar, or rather B, and then we have to initialize it. This prevents us from making it const. And I should point out that I'm using shared putter here as a stand-in for any kind of generic access that shares this pattern. This isn't just true of shared putter. This is something you need to, some resource you need to lock and then get something out of. But shared putter works well. So in C17, C++17, we got the if initializer. Of course, I know now many of you are thinking about ways that this might be rewritten. And this helps. So we can lock the thing, we can get it out. This still suffers from declaration initialization split. Although in passing, I think it likely that the if initializer will probably completely replace assignment in if conditions. We could use the conditional operator. Who likes this code? A few. So it works, and that's the best thing I can say about it. The lock lives until, the initial lock lives until the semicolon, and so there is no race here, but we're getting a double lock. This clearly isn't good. This isn't why we became C++ programmers. And this sort of indicates that, although we think of if and the ternary operator as somewhat the same, they're very different beasts, really. So maybe in C++ 20 whatever, or beyond, we would get a ternary operator initializer, like an if. This isn't real syntax today, so this doesn't work. Another way we could do this, GCC has an extension called not an expression statement, but a statement expression, whereby you can put multiple statements there, and the value of the statement expression, notice that it's in parens around curly braces, will be the last thing evaluated. This is somewhat similar to functional languages where they have a way to compose expressions, and the last one evaluated is the result of the expression. Now, I know what many of you are thinking when you see this, and probably, since we're all in this room au fait with C++, you're thinking of an immediately invoked inline initializing Lambda expression, as many eyes as you like, Lambda expression. And this might be good, depending on your code base style. This avoids the initialization declaration split. This allows us to make B const, although I didn't put it up here. So this is a pretty good alternative. Another thing we might consider, though, Simon's looking at me, is an optional like. An optional like interface on our object managed by the shared putter, right? But this is hard to make generic like this because we've put the name of the variable in the function. And until we have reflection, we can't really parameterize properly over this. But I know what Simon's thinking. We might want to make a functorial or monadic interface to our shared putter, effectively turning that into a functor. Some code bases might like to do this. This would certainly be more declarative, would allow us to achieve that split. I don't think many code bases would prefer this over the immediately invoked Lambda, but it's another possibility. Note here the no discard attribute. This is another piece of imperative safety gear that we have in the language that's preventing us from discarding the result and helping us avoid the pitfalls of statements. It's effectively turning the result of this function into an expression that we can't ignore. So, okay, so this was a declarative study. I wanted to present a few different options, but what can we say about this? I think, what I said at the top of the talk was this isn't a functional programming talk. The idea here is that C++ is what it is. It's a goal to make a more declarative style, but it's not, we shouldn't go for a totally declarative style. That wouldn't be C++. But it's always a reasonable goal to improve our code with a more declarative style. And there are definitely some features of C++ that help along with that. Now, different domains lead toward different approaches. So let's take a look at some existing declarative practice. Because, as I said, we have a lot of guidelines, idioms, and if we look through this declarative lens, we could try to tie it together. Now, the core guidelines, here's a selection of them. Some of them are things we've been doing for years, like ES21. You know, that is what differentiates, one of the things that differentiates C++ from C, that we don't have to declare a variable before we use it. So we like this idea of a declarative style, not late declaration of variables when we're ready to initialize them. And you've heard a lot at this conference and other conferences, I'm sure, about guidelines. In particular, these sorts of things tend to crop up again. The idea of making variables const, making variables immutable. In fact, don't they say the same thing, con1 and con4? I guess maybe they do. And you know, ES21, ES22, and we saw the immediately invoked Lambda, which is gaining a lot of popularity for so-called, you know, complex initialization, if you like. If you watch C++ Weekly, for example, you'll see a lot of, you know, Jason espousing a lot of this sort of thing. So a more declarative style leads us to issue guidelines, assignment. Yeah, so assignment, I'm saying, you know, I've attacked that enough. I'm going to move on to the other things now. You might think that, you know, it's kind of important that we have whiles and ifs and returns and you know, jump statements and all the rest of these things in the language. So, iterations and jump statements. Well, in large part, these sort of come under attack from the thing that we like to do, which is put things in functions. We like to put things in functions, give things a name. These are all great reasons for liking functions. Scoping is a great reason. Naming is a great reason. There's another particular reason that I like functions, which is, you know, what do functions do? Functions turn statements into expressions. They allow you to take those statements, lock them up inside something that has a name, and when you call that function, the function call is an expression. It returns a value. Yeah, return is a socially acceptable go-to, if you like. And just a note on that, I'm not a fan of one exit path per function. I mean, I think that's an anti-pattern in C++. That's fairly well known. We have our RAII, so we don't need to do that kind of thing. A historical note, I looked on Stack Overflow about this notion of, because some people have coding guidelines, maybe in C++, but more so in other languages, I think, where they say, oh, our coding guideline says we're only allowed to have one return statement per function. So I tried to figure out where this came from. And if you go back to looking at Fortran, well, it turns out this came from structured programming. Now, the notion of single exit was introduced with structured programming as a guard against alternate returns. Now, in Fortran, it wasn't that the returns were from multiple places necessarily, but they were actually returned to multiple places. Because in Fortran, when a function had an error, you could have an alternate return that returned you to a different place where the error was handled differently from where you called it. So there was the potential in Fortran to get really confused with these alternate returns. And I think that's what structured programming introduced the notion of single return to get around. And that kind of, over time, got morphed into this idea that, well, we should only have one return from a function. I don't think that's right, you know. And in C++, we know that's not right. So we like functions. We like algorithms, of course. We know this guideline, no raw loops. What does no raw loops actually mean in a declarative style? It means we're encapsulating those iteration statements. We're encapsulating those remaining assignments that happen as we go through the loop. Those jump statements, those breaks, those continues, they all get wrapped up into an algorithm. And so no raw loops as a goal, is a subset of strive for declarative code. Here's a selection of algorithms in my toolbox. None of these is particularly groundbreaking. Some of them, many of them, are little more than rebrandings of one-liners that use STL algorithms, and none of them is more than a handful of lines. But what they do is avoid statements in logic. They simplify control flow, they help me at my call site, and they deal with all the edge cases, of course, because well-written algorithms deal with edge cases. They take edge cases out of your business logic and push it down so you don't have conditions, you don't have loops at your call site. So, no raw loops leads us to avoid iteration and jump statements. Initializing lambdas, initialization guidelines lead us to avoid assignments. Let's look at how to avoid conditions, because that is not nearly so obvious. But we're already doing it. And let's take a look now at more object-oriented style, if you like. We'll get there in a slide or two. Testing is a great example of where it's a very declarative style. We use macros typically, and global state, but that isn't so bad. Sometimes you have to do what you have to do. And remember, C++ is a multi-paradigm language. But what we get here is idempotency. It doesn't matter how many times we put these require statements in or what order they come in. There's no dependency between them. We're leveraging our AII. We're doing things declaratively, and we're seeing the rise of the popularity of sections for testing rather than fixture management, which is along that style. Let's look at a case study of, I thought I'd look at logging, because that's sort of a very, very imperative style thing. But I think I can show you a way in which it's turned declarative. So the top line is, C. It's how we might do logging in, let's say, 1980. And the bottom line is how we might do logging in a typical C++ code base today. Many of you perhaps have code that looks like this, where we leverage the output stream operator to build the log line. That's a very, in its way, that's a very declarative style. We're using overloaded operators. We're using an expression to log rather than a statement. And we've got extensibility there because we can provide that operator for our own types. We're not limited to the set of formatting that happens in printf. Now, we also get, of course, safety, because we don't have to make sure that the number of arguments matches up with the number of format specifiers. Usually the worst we can expect from the bottom is that we get unexpected conversions of the arguments. Usually it won't actually crash our code. So that's better. But I hear you say, there's a global variable in the top there. There is a global somewhere in the bottom. Where did it go to? Well, it's still there. It's still there. That's okay. It fundamentally, at least in the logging frameworks I use, there's the idea of a log sync. And if you write a log line, it goes to a log sync. And that might be a file, a log over the network, what have you. So let's look at the C-style log sync, right? If we wanted to do this in 1980, gdebug log file p there is a file pointer. In 1980, in the late 70s, if we wanted to change where this went, well, we'd probably do it at the shell. We'd go to, we'd have stood out, we'd tee it to somewhere, we'd pipe it to somewhere. That's fine if we're using small console apps, but if we're doing larger applications, we want control, we want the ability to wrangle logging at runtime, we want all those things. And in C, we'd likely encapsulate that in our own function. What would we do in object-oriented style? Well, we'd have perhaps something like this idea of a log sync, where logs go, and it pretty much has one operative function. We can push a log entry, and it returns a bool, you'll notice, and that tells us whether or not that sync accepted that log entry. And using just this single function interface, this is an example of applying declarative style to a traditionally object-oriented approach, because this gives us compositionality. With just this single function interface, we have quite a range of choices in syncs we can make. For instance, we can make a sync that goes to a file, and we set it up with a path name. And then when we push to the file, it writes to the file. When we push to that file sync, it writes to the file. Same way we can make a debug sync, outputting to the debug window. Or maybe a network sync, listening to a log aggregator service that we have. So we can put it to different places. But we can also write a sync that filters. We can have a predicate that's looking out for certain things in the log line, certain ways we mark it. And this is where that bool comes in. So we can say whether or not this sync accepted the log line. We can also wrap it with an execution policy. So we could have a multi-threaded log. We could take our sync, any one of those syncs that we've said, and just wrap it with an execution policy so that we can get deferred logging to a file or deferred logging to a network. We can make a sync that encapsulates multiple other syncs. And notice here that I'm not really using any modern techniques. This is plain old object-oriented class hierarchies, virtual functions. This is stuff we've known how to do for a long time. I just wanted to show you this because I think getting the interface right for compositionality leads us towards this declarative style, even when we're working in object-oriented style. It's what we're doing already. So we can make this multi-sync, and because the syncs return the Boolean as to whether they accept the log line or not, we can parameterize this multi-sync on whether it fans out to all of the syncs it knows about or whether it will stop at the first one that accepts it. And perhaps most important of all, we can make the null sync, which just eats its input, always accepts it. So we could turn that off at runtime using a null sync. So what's the goal with all these variations? Well, this is good object-oriented design. This is tell, don't ask. This is encapsulating conditions using polymorphism. That's what good object-oriented design does. When we make syncs, we can do it in this style. We encapsulate the condition at the point of construction. We don't have to have conditions in the code whenever we use a log line, like we would in the C style. The point of use becomes declarative. So this is good OO style, and this is good declarative style. So declarative style, using a conventional interface structure, conventional object-oriented techniques, declarative style isn't about functional programming. It isn't about value types. Of course, you could use an alternative form of polymorphism. You could use type erasure. You could use static polymorphism. It's the same point. We're encapsulating the condition inside the class. We're pushing the choice up the call stack, removing the condition from the code that uses the object, giving the choice to the user of our library who's making these objects. So compositional patterns like that are the object-oriented way to avoid selection statements. So I'm going to say that selection has been killed by paradigm shift, which sounds like it was playing NetHack, but all right, so that leads me, a discussion of object-oriented design leads us to thinking about design patterns. And there are several object-oriented design patterns that, if you think about them in this declarative way, lead you down this realization that they are about replacing conditions with polymorphism. Here are three that I picked out. Composite has, for a long time, been my favorite design pattern. I didn't really understand why it was my favorite until I started thinking about how it encourages declarative style. So the null object pattern eliminates conditions. It allows you to write total functions. The command pattern reifies computation. It turns behavior into something that has a type, something the compiler can reason about. And of course, composite eliminates conditions because it allows it to treat different elements of a part-whole hierarchy with the same interface. It takes away those conditions from the point of use. Now, these are three patterns. In particular, there is one pattern that comes up a lot these days in declarative style, and that is, well, we know it as the builder pattern. It's not actually the builder pattern as written in the Gang of Four book, but it's also known as Fluent Style. This idea that when we build something, we get to chain pieces of functions to build up our object. Now, here's a bad example, perhaps, of a builder pattern. And Nicolas Guillemot said about it that, well, he didn't say very nice things about it. I'm not sure I'd level buggy at this, but it's true that the backing code for this call site is a couple of hundred lines of code, right? So in general, the more code we have, the more likely there are likely to be bugs. So this is the builder pattern, but it doesn't make a lot of sense to use the builder pattern in this style to me. I'd like to present you with an idea of where I think the builder pattern is much more applicable. Here is some code that I wrote in a project I was on, which I think is a better example of the builder pattern. Now, this is hopefully, this is easy to read. I'm making a schedule. I worked as a game industry network programmer for 20-odd years. My bread and butter was doing things like exponential backoff, retrying network things like that. And so I wanted to do this all over my code base. I wanted to do things like this. So the builder pattern works well, not when we're building something at the start of main, like the glut example, which we do once, but when we have something that we're doing a lot of times. Notice also here that there are relatively few verbs. There's just then. I'm not saying with X, with Y, with Z, do A, do B, do C. I'm saying there's one verb. I'm building something, then. I'm using strong types, and in particular, I'm using types which are relatively concise to write in terms of R values. So Fluent Style encourages this R value usage, which is very useful when we can make it limited in verbosity. And it's useful when we won't ever really need L values. I would have no reason to make an L value thing representing a random exponential backoff here, because all I want to do is use it immediately. So the schedule here is correct by construction. It has good readability. I think it's a good usage of the builder pattern. Now with C++17, we get a bit of extra help in using the builder pattern because we get evaluation order guarantees, which mean that each successive dot has the right sequencing of evaluation. There's another particular case I want to bring to your attention, which is using strong types in the builder pattern. So if we had a network request, typically it might have a couple of required fields and then a bunch of optional fields. And we'd like to write something like this, perhaps, where we set the fields. And we want to send the request. But we don't want the send request to work unless we filled in the required fields. So how can we do that? Ideally, we'd want it to fail to compile. So normally, we might write this as, in the Fluent style, we'd have our member functions returning references to this so we could chain them. How can we use types to make request fail if we didn't set the required fields? Well, one way to do this, and we want setting the required fields to be idempotent probably, one way to do this is to say, let's represent the setting of the fields using a bit field. So I'm going to represent all optional fields with 1 bit and the required fields with a couple of other bits. And we're going to encode which fields have been set in this bit field. And then we're going to use the properties of inheritance to build our class. So we're going to put a non-type template parameter in this class, which is going to be the bit field, which fields are set. And then our base case is going to contain, our 0 case, that's going to contain all of our fields and our data and that kind of thing. And then in our derived classes, we're going to write our set functions such that when we call them, they return the class below them in the hierarchy, or the class with that bit cleared. And it seems like this is happening backwards, but that's just because of the way that inheritance works. You can cast implicitly to a base, of course. So when we set field 1 and set field 2 here, we end up clearing the bit for field 1 or field 2, and then we use the return type there to capture that. Now we can write send request. And what we need to do here is basically delete everything for send request, except we're going to accept the request which is properly formed, which has all its required fields set and only its optional fields left. And you can see an implementation of this idea by Tim Teatro. He's at Timtro on Twitter. And at that gist, he wrote a really nice write-up of this, which happened to come to my attention just after I gave this talk in Aspen, and we talked a little about it. So that's a good example of putting the types to work, helping us with declarative style. So Fluent Style, this builder pattern, is more suitable, rather than that glut example, when you have just a single verb or a couple of verbs that you're using, when you'll be using it a lot throughout your code base. So it gives you that opportunity to exercise that declarative style in multiple places, when you can make types work and when your R values are going to be usable and not too verbose. Okay, so where is C++ currently giving us good support for declarative style, and where can it be improved? Well, one obvious place that, again, we love and we know is RAII. It's kind of the bread and butter of C++ programming in terms of resource management, and it's a very natural fit. Now, it's been truly said that initialization is a topic for experts in C++, but I honestly believe that it's getting a bit easier for everyday usage, in particular with aggregate initialization and things like the rule of zero. And UDLs and class template deduction are also great for that. So although initialization gets some bad press, I genuinely believe it's getting better. And in C++ 20, we're getting the designators to help us with that as well. I mentioned functions and lambdas. They turn statements into expressions. That's what functions do. They give them names, they encapsulate conditions, they allow us to lock up all those statements, and they give us at the call site expressive declarative code. And it doesn't hurt that, of course, functions are and always have been the bread and butter of the optimizer. And now that we have structured bindings, of course, that works around return value limitations. Something else that helps is the idea of overloads, right? Overloading or templates. C didn't have this, C++ does. And this idea of enabling the use of functions without conditionals is a great help. So parametric polymorphism. Just letting the compiler choose what's right and do the right thing, rather than having to do it ourselves. This example is from Andy Bond's talk from CppCon 2016, where he demonstrated a way to make a uniform distribution no matter what type you give it. It does the right thing. Given this, it's fairly easy to write one for durations, for chrono durations. Like I said, I worked as a network game programmer for a long time. I want to be able to compute random durations to feed into that network backoff idea. With relatively little effort, based on Andy's pattern, I can write these, and the underlying type of a chrono duration is either a float or an int. I can handle both those cases. I can make it very easy at my call site to say, instead of give me a random int and then make it into a chrono distribution, just give me a random distribution. I'm using the types. I'm using the compiler's ability to just do the right thing. I'm taking the conditionals out of my call site. I'm taking the assignments out of my call site, and I'm just making it declarative. So in 17, of course, we gained if and switch initializers, and they're great. And as I said, I think that's going to largely replace the assignment in the if condition. But we didn't get the expression equivalent of if, the ternary operator. We didn't get any love for that. Again, there's no way to do this on the bottom yet. I hope one day there may be, but I'm not holding my breath. The reason for this partly that we didn't get parity between them is because if is a statement, so if doesn't actually need to obey the rules of the type system. its two branches can be completely different types. There is no control over that. Whereas ternary operator is an expression, it needs to have a type. Anyway, I talked a little bit in my operator overloading talk about this. I'm not going to cover it in too much detail now, but operators are simultaneously great because they're the building blocks of expressions and they help us with all kinds of things declaratively, and poor because we get so little control over what we can do with them. But they can be really good for expressivity, putting together expressions, declarative constructs. Now, I mentioned imperative safety gear earlier. This is something we have a lot of in the language. So we're always getting better warnings, putting paid to things like Yoda conditions, like I mentioned earlier, where you have to reverse the order of things because one of them's a constant you don't want to accidentally assign. That's the Yoda condition if you're not familiar. Of course, we got static analysis, getting better all the time, helping us to avoid some of the obvious historical errors. We get things like the no discard attribute. If you were here for Jason's talk before lunch, he mentioned no discard in the category of things in C++ where perhaps we got the defaults wrong. I would strongly think about trying to apply no discard to all of my functions and just seeing what the compiler said. That could perhaps be another default that's the wrong way around. We get the full through attribute, helps us guard against mistakes, again, in statements, in switch statements in this time, and the if initializer. So all this stuff helps us deal with statements. The idea of this talk is to try to convince you that you can use this stuff, yes, but you can also use expressions and try to avoid statements in the first place. Something else we're beginning to get, and this is something that is not obvious at first glance. There are helper functions in the standard library, especially in the standard library, because they tend to come from the realm of meta functions. And if you're a template meta programmer, you're fairly used to programming in a declarative style, in a somewhat functional style. But if you're not used to that, then you look at some of these functions and you think, why are they useful? Well, the answer is they become useful when you try and think about things declaratively. Things like std exchange, things like asconst, things like apply. These are all functions that do relatively minor things, and until you think about your code in a declarative way, trying to avoid the use of statements and trying to make declarations and expressions do the work, some of these things, they aren't obvious what their use is. But I'm happy to see more of them entering the library, and they are supporting declarative constructs. Of course, I put in that category also expanding type traits and a possible monadic interface that's optional. Simon. So when you start trying to deliberately limit your use of statements and rely more on declarations and expressions, the use of these things becomes more apparent. Here's a couple of examples. When you first see identity, you would think, what on earth is the use of that? There's no possible use in my imperative code, in my object-oriented code. Identity was, in fact, in the original SGI STL. It was left on the cutting room floor in 1994 or so. So, yeah, here's a couple of examples. Always is a function that returns a function that whatever you give it, it'll just return what you gave it first, right? You build a function that returns the same thing all the time. Again, hard to see the use of that until you start trying to piece together things declaratively and use expressions. Okay, so having said all that, what are some guidelines I can give for declarative code? Well, as I've been saying, principally, we should avoid writing control flow and assignment statements where we can. And that means replacing conditionals a lot of the time. Now, I've put in this table four entirely different programming styles, but each one has a strategy for programming declaratively. So in the imperative style, the signature element is the statement, right? This is what we're trying to minimize. Now, actually, the elimination strategy at a C++ high level is not often used, but this, a lot of times, comes up at a very low level. right? So the strategy is basically multi-computation. And we see this, when the compiler, for example, replaces branches way down deep in the code, or when we use intrinsics to avoid branches, perhaps. So relatively rare in higher level C++ code, but it does exist. In object-oriented paradigms, of course, our signature element is the construction of the object. And as we saw, the strategy for eliminating conditionals is encapsulating with polymorphism. So we get things like the null object pattern to turn things off at construction rather than having the conditional at the point of use. In a functional style, you can probably guess what I'm going to say here. The signature element is the function call. And how do we get rid of conditionals? We put them in functions. It's all about functions. But in a generic style, our signature element, this is very much like the object-oriented style. So if object-oriented is the dynamic polymorphism, then the generic style is the static polymorphism. So instead of object construction, we have type instantiation. And instead of polymorphism, well, we have static polymorphism or traits classes, things like that. So all of these things, these elimination strategies, you're looking at this, and this is kind of, object-oriented 101 perhaps, or generic programming 101. But when we look at it through a declarative style, we can see that all of these things are in fact towards the same end. They're trying to eliminate statements. They're trying to encapsulate that problem that we get when we have to reason about sequencing statements, turn that into expressions and things that the compiler can reason about. So this, if you like, is the conditional replacement metapattern. So what happens when we replace conditionals? Well, we end up either pushing them up or down. If we push them down the call stack, what we see is embodiment in data structures where the conditions are somehow intrinsic to those structures. We see things like optional or monadic interfaces to things like optional. We see things very much similar to how when we think of handling errors, that we should handle them at the leaf of our code and not leak them up the call stack. Encapsulation in algorithms, things like that. When we push them up the call stack, well, we call that things like dependency injection. We call it higher order functions. What we're doing is giving the power to the caller to make that choice at construction time, at the time before the use down in the code, and it's abstracted away that condition to lift it up. And either pushing down or pushing up, as I said before, that can happen in whichever way is right for your programming paradigm, but it can happen. And the goal here, if you're sort of thinking about this in a functional way, you'll see that the goal of both of these things is total functions. That is, functions that have wide contracts, functions that we can call no matter what we have on the input, they will do the right thing because they've been constructed in the right way. Either they're encapsulating some condition and dealing with it, or we've already made that choice. So when you do this exercise of replacing, in particular, conditionals, the gain is you get better call site logic, you get simpler functions, you get simpler loops. You are able, and the compiler is more able, to reason about your code. And so that's the case when we replace conditionals, and it's a very similar story when we replace loops. Again, the list here is almost the same. And also, when we encapsulate things in functions, we get a bigger vocabulary. When we replace assignments, we get declaration at the point of use. We get power in building things. If we use operator overloading, if we use user-defined literals, we get the ability to leverage const. We get the ability to make things simpler at the declaration site. We get to leverage the power of return. And where we can't avoid statements, we always get to fall back on this imperative safety gear. The language is giving us more of this every day. in the form of attributes like no discard, in the form of if initializers replacing the assignment in if expressions, in the form of static analysis, in the form of all the tools and contracts and everything that we've been working at these last 5, 10, 15, 20 years. When we have declarative interfaces, they look like this. They look easier to use. We give our users the ability to inject their dependencies to either by a class in the object-oriented style or by a function if we're in a function style. We give them the ability to construct objects easily with a builder pattern. As library developers, it behooves us to identify our monoids. In particular, if I could give one tip for being a library developer, that would probably be it. And that if you can do that, that enables your users to get so much for free. If you can just give them that power, the power of the monoid over your types. And a lot of times, it all starts with thinking about how compositionality works. How a user is going to use my library so that they can compose things together, so that I can give them the power to make choices and to build things up. So my goals for declarative code are these simple goals: favoring expressions over statements, favoring declarations over assignments, and striving for unconditional code. Thank you very much. There is a question.
Question, in your example with building the request type, with the required and optional fields, why didn't you just take the required fields in the constructor and delete the default constructor?
Ah, yes. So in my, I can't remember where it was now. Oh, I think I went past it. In my builder pattern example, here, somewhere around here.
Yeah.
Why didn't I just pass the required fields in the constructor? Yeah, that's totally an option. Sometimes I want to be able to partially construct a request and pass it down to something else that wants to construct more of it. So yes, if you can put them in the constructor, that's a great option, of course. But I wanted to, partly I wanted to show this technique in the talk. And sometimes you want to construct things over time. Sometimes you know something at one site and you don't know other things. So that was the reason.
Hey Ben, and
hey.
One of the last slides you had, I think it was your second last slide, it was all about what the declarative style helps you with.
This one? This one?
Yes. So you say that it helps you identify the monoids among your type system. I wonder if you could expand exactly what you mean by that.
Okay. Identifying monoids as a writer of a library or code that someone else will use, identifying monoids in your code, in your types and your operations, I think is one of the single biggest things you can do to help users of your library. So it's thinking about compositionality. Anytime you are composing any two objects, just ask yourself, is this a one-off composition, or is there actually a greater structure to this? Because if I can identify, I have a type, and under this operation it forms a monoid, then I can use that to flesh out my design space. I know what operations make sense. I know perhaps things that can build on that. I can enable my users to use fold expressions if I choose to overload an operator. I can enable them to use things like accumulate and reduce. I talked a little bit about that in my operator overloading talk. But talking about monoids and type design in libraries is an entirely separate talk. But that's just a little of my thought there.
Yeah, that's great, thanks.
Thank you.
So when I've tried recommending people start adopting declarative style programming, I'm often met with resistance of people saying, well, this code, which is currently in imperative style, is currently clearly obvious what is happening, and why should I change it to something that I am not familiar with and no one else is going to be familiar with? And So I'm wondering, what kind of approaches do you use to show people who might be resistant to declarative style programming to help them understand that declarative style programming is indeed powerful?
Okay. In response to this code is unfamiliar, that argument, I usually say, humans are good at learning, and familiarity is only 2 weeks away normally. And then I would just try and give the arguments that I really hope I've given in this talk, which is that declarative style gives more power at the point of declaration. It gives more power to users of a library or a type. It reduces the cognitive burden, even though the syntax of the code might not be familiar to you today. The cognitive burden it takes off in terms of having to reason about how state flows through your assignments and whatever, more than make up for that. And it'll be familiar to you after you've used it for a week or 2 weeks. That's what I would say. Thank you. All right, thank you very much. We're officially out of time.